Welcome to Crown's e-learning course on chart interpretation. Please adjust the volume on your computer now so that you can hear the sound of my voice. Ensure your computer speakers are turned on, as well as within Captivate by clicking here. You can navigate through the lesson by using the control panel here on the screen. Thank you and enjoy the lesson. The goal of this course is to give you enough knowledge to understand and interpret basic SPC charts you will find in our plants. This will include content on histograms, standard deviation, process capability, and control charts. Histograms. Maybe you've heard of these before, perhaps seen them from time to time, but what are they exactly? A histogram is a collection of raw data put into bar graph form. It gives the user a much more visual representation of data versus scanning raw numbers. We can learn a lot about a group of data put into histogram form, such as where the data is centrally located and how spread out the data is. Take this data of plug diameter measurements. We have 5 readings taken per measurement as denoted by the columns 1 through 5. There are 12 total cans measured here, as there are 12 rows of data. What happens when we take these 60 data points and put them into bar graph form? This histogram represents the 60 data points from the previous slide. Histograms are not charted by time or date like many other charts. The x-axis is made up of bins that break up the total range of data points into individual columns. As you can see, the bins are set up by divisions of 0.1 inches. The lowest bin value is 1.4 inches and the highest is 2.3 inches. So we know all the data in our data set is between 1.4 and 2.3. The y-axis is used to show the total number of data points that fall within each bin. We can see by the tallest bin that there are more data points that fall between the values of 2.0 and 2.1 than any other range. Here is our same data set, but now the points that fall between 1.9 and 2.0 are highlighted. If we count these up, there are 14 data points that fall between that range. If we go back to the histogram, you will see the bar for the bin that represents 1.9 to 2.0 is 14 units tall according to the y-axis. This corresponds to those 14 data points in our data set. Here is our histogram with the 14 unit bar highlighted as discussed in the previous slide. This same histogram now has a line attempting to fit the data, as well as lower specification and upper specification lines as seen here. There is a second set of lines, these with dotted lines, with the designation of minus 3s and plus 3s, which stand for the minus and plus 3 standard deviation lines. These represent 3 times the standard deviation distance away from the mean or average of this particular data set. The mean here is 1.94262, while the standard deviation is 0.16306. The calculations here show the 3 standard deviation limits. Ideally, the 3 standard deviation limits will be inside of the specification lines, but here we can see the negative 3 standard deviation line is lower than our lower specification line, which means a significant amount of data will be below the lower spec, which is not good. This is the reason for the CPK capability being low. As we can see here, it is below 1, which is also not good. The higher the CPK or PPK, the capabilities, the better, with a minimum of 1.33 being ideal. Standard deviation will be explained in more detail with the next few slides. The standard deviation can be calculated by the formula on the screen. We will break this formula down step by step in the next slide. The big takeaway here is to understand that standard deviation is the average amount an individual data point is expected to differ from the mean. So data that is very spread out or with a very large range will have a larger standard deviation than a data set with much smaller range. Here is a brand new data set with the raw data on the far left column with 9 individual numbers. If we add all these together and divide by 9, we get the average of the data set, which in this case is 5. Subtract the average from each data point and we get the next column on the right. For example, the top row, we take 6 minus 5, which equals 1. We then square that column to get rid of the negative values, and we're ready to plug into the formula and get our final calculated standard deviation of the data set at 1.732. In other words, the average amount each data point is away from 5, the average is 1.732. Here are the same data points from the previous slide put into a run chart. The center line is the mean, or average, in this case 5. The plus minus 1 standard deviation lines were added as highlighted. The number next to each red dot is the amount each point is away from 5.0. This chart shows a normal curve plotted with our same data points placed inside of the curve where they belong. Again, the normal curve is centered around the average, in this case 5. In a perfect normal curve, 68% of the data will be contained within plus or minus 1 standard deviation, or 34% on the positive and negative side of the curve. When we add 1.732, which is the standard deviation, to 5, it equals 6.732, which is labeled in our plus 1 standard deviation line. Similarly, when we subtract 1.732 from 5, we get 3.268, which is labeled as the minus 1 standard deviation line. Moving out to 2 standard deviation, 95% of the data will be within these limits. And finally, 99.7% of data under a normal curve will be contained within the plus or minus 3 standard deviation limits. This 3 standard deviation limit will be discussed and used later during our discussion of control charts. There is a difference between process capability, CP, and the process capability index, CPK, which will be discussed here. There are 3 formulas shown. First, the formula for process capability, which is calculated by taking the upper spec limit and subtracting from it the lower spec limit, then dividing by 6 times the standard deviation of that data set. What this is ultimately doing is looking at how big the spec range is compared to the spread of the data. The larger the spec range, or larger the numerator, or a very small standard deviation, which would reduce the denominator, both of those will increase the process capability value, which makes sense. Process capability does not care where the data is in comparison to the spec range, for example on the high or low side, just how big the two values truly are. Another way to think about CP, this is the best you can do if your data is centered exactly on target. The calculation for CPK, or the process capability index, uses the lesser value of CPU and CPL. These two values give a capability according to each side of the specification. As we can see in the histogram, the data is shifted towards the lower spec side. This will cause the CPL value to be smaller since the mean of the data is closer to the lower spec limit. The calculations for both CPL and CPU are below. As you can see, CPL is 4.9 and CPU is over 7. The index is therefore 4.9, the lesser of these two values. If the data were perfectly centered on target, the values for CPL and CPU would be identical.
This curve shows a normal curve with the upper spec and lower spec lines exactly at the 3 sigma level, which means upper spec and lower spec are at the 3 standard deviation limits. This translates into a process capability, or CP, of 1.0. For example, if a machine is running and producing cans or ends at a process capability, CP, of 1.0, which also means 99.7% of the cans or ends coming out of this machine are within specification, this is what the data would look like in a histogram. While 99.7% sounds like a pretty high percentage, that still means that the machine is making an out-of-spec can or end once every 370 units made. When our plants produce millions every day, that adds up to quite a few defects. Now we have a normal curve where the upper spec and lower spec lines are 4 standard deviations away from the mean. This is better than the previous slide. If a machine is producing cans at this level, it is producing a process capability, or CP, of 1.33, which is equivalent to producing 1 defect per 15,500 units produced. This normal curve now shows data that has upper and lower spec at a distance of 6 sigma, or 6 standard deviations away from the mean. You can see now we have much more wiggle room for our data to move left or right and still remain within specification. A 6 sigma process has a process capability of 2.0, which when centered will produce at a rate of 1 defect per 500 million cans produced. The distributions A, B, C, and D on this chart all have process capability indexes, CPKs, of 1.0. Distribution A is centered, but with the largest spread of data. On the opposite end, distribution B is the furthest from the target and very close to the lower spec line, but has the tightest spread of data. Distributions C and D fall in between these two. Which distribution would you prefer for your process? Think about it and proceed to the next slide for the answer. While there is no concrete answer for this question, distribution B would be ideal due to the fact the standard deviation is the smallest. An operator could take process B and center it, thus creating a CPK much higher than 1.0. It is much harder to reduce standard deviation than it is to center a process. We will highlight a few different departures from normality in this slide. The first on the left is called a skewed distribution. This type of distribution has one tail longer than the other. In this case, the tail on the right. The second in the middle is called a truncated distribution. Truncated distributions have one or both tails completely missing. In this case, the left side is completely missing. This type of distribution can be created by manually buzz-cutting data. For example, on this slide, I would check whether the lower spec limit was right at the cutoff point of the data. The final example on the far right is bimodal, which has 2 distinct humps that indicate there are 2 distinct sources of variability within that data set. Shifting gears now, we will discuss control charts. Control charts show a continuous picture of variation in a process. It is the process talking to us. On a control chart, the x-axis is time, so you can watch and monitor the values at checks over a period of time to see how the process is behaving. Crown uses control charts for a variety of reasons. The most widely used purpose is to determine when a process needs to be adjusted and when it needs to be left alone. Control charts show the operator whether or not action is required. Just as important as the control chart telling the operator that an adjustment is needed, it also saves the operator time by showing that no action is needed and to leave the process or piece of equipment alone. Every process has some minimum random and expected variation. This variation is small and completely normal. This type of variation has no root cause and cannot be identified specifically. This picture shows expected random variation over time. The first check, highlighted in green, has data normally distributed and centered on the target. The next check and the next check continue to be centered on target with normal distribution. This type of process is ideal and predictable. The other type of variability is the unexpected type, where variation is larger. This type will have an assignable cause attributed to it, as it is not random. This type of variation can and should be eliminated. Control charts alert the operator to this type of variation. When assignable causes of variation occur, it could do a number of things to the data. First, the location of the histogram can move or shift. This would move the average of the data either higher or lower depending on how the data shifted. Secondly, the spread of data can change. This data set would have the same average, but the range could increase or decrease. Lastly, the shape of the normal curve could be affected. Assignable causes of variation can make the data move in any combination of these three things. How the data moves will give the operator clues as to what is happening. For example, if a piece of tooling wears down, the process may stay centered, but the range or spread of data will likely increase, like in the middle picture. If a new piece of tooling is used, the spread would hopefully be okay, but the location or target could shift. Here we see the same type of picture as before with checks and data collected over time, but something looks different, doesn't it? The histograms are drifting to either side of the target line, as well as changing shape. This type of process is not predictable and will produce many more defects than the previous process that was both predictable and consistent with only random variation. Let's take the same data set we used previously to make a histogram, but now an extra column has been added to the far right with the heading X bar. X bar also could be written with an X with a bar overhead, represents the average of a subgroup of data. In this case, the X bar is the average of the readings from the 5 columns to the left. So, if we added the data highlighted now in green and divided by 5, we get 2.03. As the dates increase while moving from the top of the page to the bottom of the page, dates on the control chart will go from left to right, just like how we read a book. Let's take a look at this chart on the next slide. Here is our X-bar chart plotted out. The data points are on the right side in red, taken from the previous slide. See how the data points match the X-bar values. This is the same chart, but with some new lines added. Note the horizontal lines marked UCL, standing for upper control limit, CL, standing for center line, and LCL, which stands for lower control limit. The value at which these lines exist on the chart is below, highlighted now in green. There is also a point circled with a red hashtag that is clearly below the lower control line. This is marked as such because that point is out of control on the control chart, since it is below the lower control limit. The center line, upper control limit, and lower control lines are calculated according to the data being charted and change as the data is entered. An explanation of this will be on the next slide. This slide illustrates how control lines reflect the spread of data, similarly to how histograms do, as we learned earlier. There are 3 color-coded zones on this chart, as well as a red histogram turned on its side 90 degrees. The green middle section is the spread of data plus or minus 1 standard deviation from the mean in a normal distribution. As you recall from the histogram lesson, 68.3% of data in a normal distribution will be within the plus or minus 1 standard deviation line. Likewise, the yellow zone represents 2 standard deviations away from the mean and will contain 95.5% of data in a normal distribution. Finally, the gray zones represent 3 standard deviations as marked in blue lettering, and these are the upper control limit and lower control limit values. As marked on the graph, 99.7% of all data in a normal distribution will be within this plus or minus 3 standard deviations from the mean. The mean of the data is the center line. So, when a point on our X bar chart goes outside the control limits, there is a 0.3% chance of that happening randomly. That is why we react to out-of-control points on control charts. The likelihood of it being random is very small, and it is much more likely to have an assignable cause. Now that we've discussed the top part of our control chart, we will move into the R, or range portion, below. Here we have the same data used to create the X-bar data, but instead of calculating the average of the 5 columns, we will find the range. Range is the maximum value subtracted from the minimum value. For example, the top row. The highest value, or max, is 2.25, and the lowest value, or min, is 1.65. The difference between those two values is 0.6, which is the range of that subgroup of 5 values. The further apart the max and the min is, the larger the range. Ideally, we want a zero range, which would be consistent measurements and is a much more stable process, but that is rarely the case. If we perform this calculation for all rows and plot, we get the range chart, which will be shown on the next slide. Here is a plot of the range data. Notice there are upper control and lower control lines on this plot as well. The lower control limit on a range plot is always 0, as you cannot have negative range. Just like the X-bar chart, there is an upper control line that shows whether the range is statistically okay and in control, or whether it is out of control and action needs to be taken to investigate why the high range occurred. Here are the two plots together, X-bar on top and range on the bottom. The points lined up vertically with each other are from the same subgroup. Notice the point out of control on X-bar with the red hashtag has a relatively small range. This suggests that the machine is precise but not accurate, and perhaps a shim needs to be placed in the equipment to move the target. Here we have the same chart, now with the trend line showing the correction after the out of control point on the X-bar chart. Notice how the points after came back into control, which is what we want. Also notice what happened on the range chart for the same points with the trend line going downward. The range went down and improved. It is likely a machine part was changed or fixed that allowed the equipment to produce on target and with a tighter range, both things we like to see in our process and SPC chart. The next series of slides will show visually how an X-bar chart and range can vary on the left side, while another visual representation of data points for each subgroup are on the right side. This slide shows points that are off target with a good, small range. There are out-of-control points on the X-bar, and all points are in control on the range chart. This is shown visually on the right with tight histograms showing a small range, but the histograms are moving around a lot top to bottom. Here we have the opposite of the previous chart. The data target is centered, shown both by the X-bar chart being in control, as well as the histogram centers all being in the center line. Now the problem is the histograms are much larger and more spread out, showing that there is a bigger spread in the data. This results in a larger range and is shown by the out-of-control points in the range chart on the bottom. This is a critical concept to understand with an X-bar R chart. You should first look at the range chart to see if everything is in control, and then look at the X-bar portion. For example, look at the data in the window. Both of these data sets have the same exact average, but drastically different ranges. This is exaggerated, but demonstrates how averages can be the same with different ranges when using an X-bar R chart. This is an example that you do not want to see on a control chart. The data is not only bouncing around the target, but has a very large range. This causes both the average and the range portions of the chart to have out-of-control points. This could have multiple root causes that need to be investigated. This process is ideal where both the X-bar and range are in control. The movement in the chart is caused by normal variation in the process. When control charts look like this, there is no need for adjustment to the machine. Another type of control chart frequently used is called a median and individual chart. This type of chart plots the individual points for each check in a vertical alignment. The line connecting check to check is the median point. Both the individual points and the medians have control limits that must be in control. The control limits are calculated the same way as an X-bar. This concludes Crown's chart interpretation course. Thank you for your participation.